Let's learn about a special continuous distribution called the normal probability distribution. The normal probability distribution is one of the most commonly talked about distributions. Why? Because most continuous variables that are common in business have distributions that closely mimic or resemble the normal distribution. The normal distribution can also be used to approximate various other discrete probability distributions. You have already seen how we approximate the binomial distribution using the Poisson distribution when we talked about discrete distributions. But now we can also use the normal distribution to approximate other distributions. The normal distribution provides the basis for classical statistical inference because of its relationship to the central limit theorem. So when we do calculations, the central limit theorem will be very useful, and the normal distribution helps us to connect the central limit theorems to our problem. Now this is the normal probability density function, the PDF of the normal distribution. F of x is equal to 1 over square root of 25 sigma times e to the power of minus half multiplied by x minus mu over sigma whole thing square. So e is a constant and it has a value. Phi is also a constant and it also has a value. Mu stands for the mean of the distribution and sigma stands for the standard deviation of the distribution. Capital X can take any value between minus infinity to plus infinity. So this is the PDF. You can see the probabilities of the random variable capital X will be dependent only on the two parameters mu and sigma. So we often say capital X is distributed as normal with parameters mu and sigma. This is how we would denote that. Every time you specify a particular combination of mu and sigma, you will get different normal probability distributions. So previously we have discussed the properties of continuous random variables commonly, but now let's particularly look at the properties of the normal distribution. So again, total area under the normal curve is equal to 1. So the curve of the PDF is called the normal curve. This curve is symmetric around mu and the area to each side is 0.5 because the whole area is 1. So it's symmetric along mu. So one side area will be 0.5. The tails of the curve extend up to infinity, minus infinity and plus infinity. Each pair of values for mu and sigma determines a different normal curve. So if you can see here, mu is the same for both these curves, but sigma is different, right? The curve with sigma equals 2 is narrow, and the curve with sigma equals 4 is much more wider. And if you look at here, the two curves are for normal distributions with the same sigma but different mu values. So this is 66, mu equals 66, and this one mu equals 70. So the highest point on a normal curve occurs at the mean. The mean, median and mode are all equal. The mean locates the center of the curve and can be any real number. It can be negative, positive or 0. The standard deviation, sigma, is always positive and it determines the shape of the normal curve. The larger the standard deviation, the wider and flatter the curve. 68.26% of the area under the curve is within one standard deviation of the mean. So if you look at this curve, so if I mark, this is where mu stands. 68.26% lies within one standard deviation of the mean. So if this is sigma and this is sigma, so this area inside one standard deviations within the mean will constitute 68.26. That means 0.6826. That would be the probability, that is the area within one standard deviation from the mean. Similarly, if you calculate two standard deviations within the mean, the probability would be 0.95, and three standard deviations around the mean would be 0.9972. So those are the properties of the normal probability distribution. So let's do an example. Suppose, usually from by analyzing previous results, we know that SENG 11243 exam marks will follow roughly a normal distribution, and the mean would be 60 and standard deviation would be 50. What is the probability that a randomly selected student will score less than 50 marks? Second part, will score between 60 to 75 marks. So we know that the marks follow a normal probability distribution, right? So what would be the range of the marks? Usually the marks will start from 0 and it will go up to 100, right? So we know it will be between 0 and 100. This would be 0 and this would be 100. So this has to be symmetric. When you draw, you make sure that it's symmetric. And they are asking what is the probability that it will be between less than 50 marks. So the mean is 60, right? What is the probability that marks will be less than 50? So probability that capital X will be less than 50, right? So how do we calculate this? Now to calculate normal probabilities, we have an Excel function. So we have a function in Excel called the norm.dist function to calculate normal probabilities. The parameters of this function are X, the value, mean, standard deviation, and whether this is a cumulative probability or not. So in our case, we want X equals to 50, mean equals to 60, standard deviation is 15, and yes, we want to calculate probability X less than 50, so cumulative yes. So the probability that a given student will score less than 50 marks is 0.25. Then what is the probability that the marks would be between 60 and 75? And then what is the probability of getting a mark between 60 and 75? So if this is our probability density curve, right, this is X, this is f of X, and this is our curve. So this is 60. I want to know the probability of getting 60 and 75. So the area of this region. So the probability of this region. Probability that X is greater than 60 and less than 75. So how do we do that? This is simply equal to probability x less than 75, this whole area, minus probability x less than 60, right? So this would be norm dot dist 75, 60, 15, 1 minus norm dot dist 60, 60, 15, 1. So norm dot dist 75, 60, 15, 1 is 0.841345. Norm dot dist 60, 60, 15, 1 is 0.5. And the probability that a randomly selected student will score between 60 and 75 is 0.3413. So you should note that this is the probability of the random variable taking a value less than the mean. So we have previously discussed the probability density curve is symmetric around the mean. So you can see here also that because of that reason, this probability is 0.5. Now let's look at another example. The heights of men are normally distributed with a mean of 175 centimeters and a standard deviation of 7 centimeters. The question is, what proportion of men are less than 180 centimeters? So how do we put this question into mathematical equation? First of all, what they are asking is, what is the probability that capital X is the height of men? What is the probability that capital X is less than 180? So again, we use the norm dist function where x is 180, mean is 175, standard deviation is 7 and cumulative true. So that value will be given as 0.76. Next question, what proportion of men are more than 180 centimeters tall? So now we are asking, what is the probability that x is greater than 180, this small area? So when we have to calculate greater than probabilities, we take the complement. We calculate 1 minus probability x less than 180. So that would be 1 minus, we use the norm dist function. Norm dist, x is 180, mean 175, standard deviation is 7 and cumulative true. So 1 minus 0.6, the probability is 0.24. So this area is 0.24. Next, what proportion of men are between 170 and 180? So what is being asked is the area of the curve between 180 and 170. So that would be probability x less than 180 minus, we take this whole area, probability x less than 180. To get only this colored area, we have to subtract this unshaded area. That would be minus probability x less than 170. So this would be norm dist 180 and the rest of the parameters minus norm dot dist x equals to 170 and define the rest of the parameters. So this would be 0.76 and this would be 0.24. So the probability of the heights lying between 180 and 170 would be 0.52. Now we are going to talk about a special kind of normal distribution, that is the standard normal distribution. The standard normal distribution is a special normal distribution where the mean is equal to 0 and the standard deviation is equal to 1. Previously, we just used capital X or capital Y or any letter to represent the normal distribution. But if we use capital Z to represent the normal distribution, then we understand that we are talking about the standard normal distribution. So the probability density function would also be f of z, and the density curve here is symmetric around 0 because 0 is the mean. So the standard normal curve is centered at mean 0 and the z-axis is labeled in standard deviations above and below the mean. So this shows how many standard deviations above or below the mean. Previously, we just had the Excel function to calculate normal probabilities. But when we have the standard normal distribution, we have a table. This is called the standard normal distribution table. This table gives a list of probabilities that shows the areas under the standard normal curve for variable z that ranges from 0 to a positive number z. Let's see how we can use the standard normal distribution table to read probabilities. So let's say I want to calculate the probability of z being greater than 0 and less than 1.65. This value of 1.65 can be written as 1.6 plus 0.05, right? So what I can do is I can locate 1.6 under the column labeled Z, and then I can move to the right until I meet 0.05 column. There, at the intersection between 1.6 and 0.05, I will meet the correct area 0.4505. So this is the area that I wanted to find as shown in this figure. So this probability I can express as probability capital Z is between 0 and 1.65, and that is equal to 0.4505. So if I wanted to find the probability that Z is less than 1.61 and greater than 0, that would be, I would locate 1.6 under Z column and move to the right until I find the column 0.01. So where 1.6 and 0.01 intersects, I will find the probability 0.4463. Then my answer would be 0.4463. So remember, in this table, it gives the probability that Z being greater than 0 and less than a given value. It always starts with 0. So how do you convert a given value of a normal distribution to its standard normal value? There is a formula. Simply, given x, you subtract the mean and divide by the standard deviation sigma. So Z equals to x minus mu divided by sigma. Now let's discuss an example. Let the random variable capital X be distributed as normal with mean 5 and standard deviation 10. Find the z scores for x equals 5 and x equals 6.2. First of all, we will write the formula for z. Z equals x minus mu over sigma. So when x equals to 5, it would be 5 minus 5 divided by 10. First one would be 0. Next one, 6.2 minus 5 divided by 10. That would be equal to 1.2 divided by 10 equals to 0.12. Right. Now, what we did here was basically we first had x like this. So the mean was 5 and the value that we were interested in was 6.2 and the standard deviation was sigma equals 10. We just converted this into the standard normal distribution where the mean was 0 and the value that we were interested in was 0.12 standard deviations away from the mean. One of the main uses of the standard normal distribution is we can compare two observations coming from different normal distributions. Let's see an example. Heights of men are normally distributed with a mean of 175 centimeters and a standard deviation of 7 centimeters. Heights of women are normally distributed with a mean of 162 centimeters and a standard deviation of 6 centimeters. Let's say Supun is 195 centimeters tall and Anjali is 180 centimeters tall. Who do you think is taller in terms of their own gender distributions? For this, we will first calculate the Z score for Supun. So, Supun's score is 195 minus the mean 175 divided by 7, the standard deviation, which is equals to 2.86. And for Anjali, that would be 180 minus 162 minus 6. That would be equal to 3. So you can see that when we look at the row heights, Supun seems to be taller. But when compared to their own gender distributions, Supun is 2.86 standard deviations away from the mean, while Anjali is 3 standard deviations away from the mean. So, in terms of their own gender distributions, Anjali is taller. So, likewise, when you want to compare observations from different normal distributions, we need to standardize the observations. Let's look at another example. The time between release from prison and conviction for another crime for individuals under 40 is normally distributed with a mean equal to 30 months and a standard deviation equal to 6 months. Calculate the percentage of these individuals convicted for another crime within 2 years of their release from prison. So, by reading the question, we can understand that the time between release from prison and being convicted for another crime, let's say capital X, is distributed as normal with mean equal to 30 and standard deviation 6. So what is the probability of a person does another crime after being released from prison within 2 years? That means, so 2 years in terms of months is 24. What is the probability that capital X this time is less than 24? So this is what is being asked in the question. So how do we calculate that? We have probability X less than 24. It's basically the area of this curve. So we calculate norm.dist, X equals 24, mean is 30, standard deviation is 6, and cumulative, yes, equals to 1. So the probability that a person does another crime between 2 years time after release from prison is 0.1586. So that is one way to calculate the probability. How do we calculate the probability? Using the Z distribution. Another way to get the probability is to convert X into Z. So what we do is, probability X less than 24 is equal to probability Z less than -1. So how do we get this -1 value? Because we convert the value into the Z value. So 24 minus 30 divided by 6, the standard deviation. So this is equal to -1. And then we have the norm.s.dist function in Excel. We go to Excel and type norm.s.dist and we enter the Z value, which is -1, and whether it is cumulative or not, which is yes. So we enter 1 and we get the same answer. So depending on the situation and the availability of resources, you can either use norm.dist function or norm.s.dist function to calculate corresponding probabilities. Without using Excel also, we can solve this problem. What we can do is, we first convert the X value into the Z value. So we are interested in finding the probability that Z is less than -1. And then we use our standard normal tables to get the value. So the probability that Z is less than -1 is given in this area. So this is the area that we want to calculate. However, when we look at the table, it defines all the probabilities between 0 and a given value. So it always gives the probabilities in this second half of the curve. We don't have any minus probabilities defined for this table. So if we want to use this table, we have to use some transformations. Right, so let's first look at our density curve. So this is our density curve and this is probability, the mean equals to 0. And this is Z equals to -1 and this is the probability that we are interested in calculating. We know that the normal density curve is symmetric. So the area to the right of +1 is the same as the area to the left of -1. So these two areas are similar. So instead of finding this area, I can find this area and that will be the answer to our question. So this would be equal to probability Z greater than 1. So we can use the standard normal table to get this probability. When you look at the standard normal table and read the value under the Z column 1.0 and go to your right and select the value under the column 0.00, we have the probability 0.3413. But according to the definition of the table, this would be the probability that Z is between 0 and 1. So the probability that Z is between 0 and 1 is 0.3413. But what we are actually interested is the probability that Z is greater than 1, this small unshaded region. So what is this? We know that the probability of this symmetric half is 0.5 because the whole area is 1, the curve is symmetric, and the area to the right of 0 is 0.5, the area to the left of 0 is also 0.5. So this whole area is 0.5. So to get this small part, what we do is, this would be equal to 0.5 minus 0.3413, which is equal to 0.1587. So using this method, we find the probability that x less than 24 is equal to probability that z less than minus 1 is equal to 0.1587. So we can say around 15.87% commit a crime within 2 years of their release. In some situations, we know the area under the curve and we are interested in finding the corresponding Z value or the X value. For example, let the random variable X be distributed as normal with mean 5 and standard deviation 10. What value of X satisfies probability that X is less than a given value equals to 0.8? So what is this given value? How do we find the given value? To calculate the value of X straight away, we have a function in Excel called the norm.inv function. We go to Excel and type equals norm.inv and it asks for 3 parameters. What is the probability that you are interested in calculating? What is the mean of the given distribution? What is the standard deviation? So in our case, the probability is 0.8, the mean is 5, and the standard deviation is 10. So when we enter those values, it straight away gives the desired X value. So what value gives a probability of 0.8? What is this X value? This X value is equal to 0.13.416. Instead of the X value, you can also find the Z value corresponding to that probability. To find the Z value, you type in Excel norm.s.inv. So the only parameter that you have to enter for that is the probability. So it asks for the probability and you enter 0.8 and it gives the corresponding Z value. So the Z value is equal to 0.8416. So you know that Z equals to x minus mu over sigma. Using this, we can find x as x equals mu plus sigma times z. So this would be equal to mu is 5, sigma is 10 times 0.8416. So from this, we can find that x equals to 13.416. So similar to the previous answer, we get x equals 13.416. So this is two ways that how you can calculate the corresponding value given the probability of the distribution. Let's look at an example. Suppose that SENG 11243 exam marks follow roughly a normal distribution with mean equals to 60 and standard deviation equals to 10. Then X is distributed as normal with mean 60 and standard deviation 10. Calculate the exam mark that the top 10% of the batch achieves. Calculate the range of marks that the middle 90% will achieve. In the first question, what is being asked is the exam mark that the top 10% of the batch achieves. So this is the probability density curve. What is the mark that the top 10% achieve? So here the area is 10% or 0.1. To the right of the tail is 0.9. Basically, what is the value of x so that the probability that capital X is less than simple x is 0.9. So we use the norm.inv function. Probability is 0.9. The mean of the distribution is 60 and the standard deviation is 10. So the value of x here is 72.82. So the exam mark that the top 10% of the batch achieves is 72.82. Or you can also use the norm.s.inv function and enter the probability 0.9 and you will get 0.1282. Then you convert it into capital X and also there you get the same answer. The next question asks for the range of marks that the middle 90% will achieve. So what is the range of marks that the middle 90% will achieve? The range, let's say this is simple A and this is simple B, lies between the middle 90%. So the rest will be 10%, and because this is a symmetric density curve, it has to be divided equally in these two tails. So here will be 5%, here will be 5%. To find this value, simple A, we can use norm.inv 0.05, 60, 10. To find this value, we can use the probability to the right of simple B is 95%, 90 plus 5. So norm.inv 0.95, 60, 10. So this value will be 43.55 and this value will be 76.45. So the middle 90% would score between 43.55 and 76.45 marks. The
binomial distribution is discrete, as you know, and the normal distribution is continuous. However, when we are performing a test and the outcome is a binomial distribution, if the number of trials is large, the binomial distribution actually starts to look like a bell curve. So, in that case, we can use the normal distribution to approximate it. So, there is a rule of thumb that you have to follow to make sure that it actually follows a normal distribution. So, we can apply the normal approximation to the binomial distribution. So, here you have to first of all check whether NP, that means number of trials times the probability of success, is greater than or equals to 5, and NQ, number of trials times the probability of a failure, is also greater than or equals to 5. If these two conditions are satisfied, you can actually apply the normal approximation to a binomial distribution. For example, let's say a factory produces light bulbs and each bulb has a 5% defect rate, right? So in a factory, a line of bulbs are produced. So when you look at every bulb, each bulb has a 5% chance that it will be defected. So quality control inspector tests 100 bulbs in a row. You need to check the probability that 5 or fewer bulbs are defective. You need to calculate that probability. So as you can see, this is a binomial experiment. You can check the 4 conditions that I have previously provided. Right? So in that case, because you can see the n is very large, you can check whether you can apply the normal approximation to the binomial distribution, because it is easy to calculate, do the calculations. So let's check. So now we want to know 5 or fewer bulbs are defective. So being defected is our success. So probability of a success is 5%. So let's check the conditions. N times P is 100 into 0.05, which is 5. N times Q is 100 into 1 minus 0.05, which is 95. So you can see both are greater than or equals to 5. So you can apply the normal approximation. Then to apply the normal approximation, you know, to define a normal distribution, you need the mean and the variance. So what is the mean and the variance, or the mean and the standard deviation? So the standard deviation is basically the standard deviation of a binomial distribution, which is square root of n times p times q, and the mean is n times p. So this is the mean and this is the standard deviation of this binomial distribution. So this experiment, right, the random variable that you are considering, the number of defective bulbs, can be approximated according to a normal distribution with mean 5 and standard deviation 2.18, right? So what we need to find is probability x less than or equals to 5, because we want to check 5 or fewer bulbs are defective. So probability x less than or equals to 5, as you know, as a fact, you are applying a continuous distribution to a discrete distribution. So you have to apply something called the continuity correction, right? You are not just checking probability x less than or equals to 5, you have to check probability x less than or equals to 5.5. You have to add 0.5. That's what you do when you have to check less than or equals. So then you have to use the usual procedure. How do you find this probability? You can use Excel formulas, or you can first of all convert it into an Z score and then find the probability that Z is less than 0.2294, right? So from the Z table, you can get the probability of getting 5 or fewer bulbs are defective is 0.5910.